Hello, my name is Pelter, and I'm presenting Nearly Unlimited Profits, accurately predicting the sales price of real estate for data mining cs5593 online version, fall 2016 for Dr. Greenwald. Presentation agenda is introduction, related work, proposed work, and results, which includes data exploration, the decision tree model that I built, selected visualizations, the UI, and conclusions and future work. Introduction. As many of you know, it costs a lot of money to buy and sell a house, but it also costs realtors a lot of money to buy and sell houses and companies, and it would be really great if we could predict accurately the final sales price of the value of a home before we actually list it. There are a lot of reasons for this. One, obviously, being the amount of time spent selling the house would be decreased greatly, which would lead to potentially greater profits for not only the realtors and the realty companies, but also the buyer or the sellers, and ultimately the buyers who become sellers, because the house would be priced at the highest point at which you could sell it. Therefore, there would be less haggling. Less time spent prepping the house, those kinds of things, and it would also potentially lead to better customer service. The real estate agents could cater more to the needs of the client as opposed to just trying to turn the house as quickly as possible. It would also lead to a lot of health benefits, believe it or not, with less stress and better feelings and better relationships between both the realtors and the clients, and also the buyers and the sellers. They could work more closely together. Believe it or not, there's actually been quite a great deal of work done in this field. It's kind of built one on top of the other, you would expect. The first iterations of it were just attempting to see if you could determine what attributes to a house determine the price, the final sales price. And then it went into predictions. It was interesting as I read through this, a lot of things that I thought might be results from the work. Actually, some other people have thought the same things and are working towards that as well. As you can see from most of the literature here that I pulled, with the exception of this one, Detriments of Real Estate Values in the Journal of Urban Economics, most of the work has been done over the last 5 years. Here's another 2002, but most of it's been done over the last 5 to 10 years, with a lot of interesting results. So, as far as the work and the results go, obviously we started with data exploration and data cleansing. The data set that I used had nearly 1,500 records. It was based out of Ames, Iowa, over a 5-year period. It was broken down to 79 attributes, and obviously the one responsive variable was the sales price. The attributes ranged from things you would expect, like square footage, type of finish, overall condition of the house, overall quality of the materials used, location, meaning neighborhood, size of the lot, to some other things that are maybe you really wouldn't think of, like relative proximity to things like railroads, highways, I believe schools, the slope of the property, really a vast cross-section of things that people may or may not look at consciously or subconsciously when purchasing a house. After exploring the data, obviously you see things with it, and we move on to data cleansing. There were actually quite a bit of NAs in this data set, but interestingly, the NAs always meant something in this data set. They were really never a mistake, and generally what it meant was that if you saw an NA, it meant that that particular property did not have that particular attribute. So for something like the garage attributes, like the size and the number of cars you fit into a garage, and square footage of the garage, if it said NA, just meant there was no garage. So instead of leaving it as NAs, I went through and reset the NAs to values that made sense, such as 0 for square footage, 0 for number of cars, no for type of garage, or none for type of garage, things like that. Beyond that, there were 5 outliers, and these were actually pointed out in the data set that instructions that Dean DeCock, the creator of the data set, pointed out, and all 5 properties were greater than 4,000 square feet. He believed that 2 were actually outliers, and if you look at the data, you can see why. They were priced very low for the square footage, or they were sold for very low for the price of square footage, and the other 3 were probably accurately priced, but they were so much larger than any of the other properties sold that it just skewed the data wildly. The other thing that I did learn and that I used in my final result set was the response variable of the sales price, and you'll see as we go through here, was skewed to the left slightly, but when I transformed it with the log function, it had a pretty normal distribution. So moving on to the actual work, I used a decision tree for this project, and I actually used the entropy algorithm as the splitting method, or the entropy formula as the splitting method. Really, the only reason I chose this was because it was the one that we had focused least on in class. It'd be very simple to switch over to Ginny or the error classification formulas. It was just something I chose to do on this one. And the stopping criteria, just like in class, every element in the subset belongs to the same class. There are no more attributes to be selected, or we reach the end of the subset. So selected visualizations. Again, here's the sales price, and like I had mentioned earlier, the sales price is skewed to the left. So transformed with the log function, and it's a pretty normal distribution here, still slightly skewed, but it's probably as close to as good as you're going to get for a true cross-section of any type of data. And I also thought the correlation matrix was pretty interesting here. You see, it looks like overall quality of the house is correlated most highly with the sales price, as you might guess, and then also the GR living area, which means basically how much actual living area in the house was exclusive of the basement and the garage. Some other things here. The garage area was pretty significant. That usually goes hand in hand with the square footage. The larger the house, the larger the garage. Total basement square feet and first floor square footage, again, go hand in hand with the living area, so it's not surprising. And you can see that they are tightly correlated as well. Year built, year remodeled. This one was kind of interesting. The mason veneer area, and actually the mason veneer type of both played a significant role as an indicator as to what the sales price would ultimately land at. For the UI, I actually used Shiny, which is an R package provided by RStudio, and it's free to use for something like this for educational purposes, but there is a fee associated with it if you productionalize your application and host it on a server. I think you get 25 hours free, and then beyond that you have to start paying fees per hour usage to Shiny. Obviously, it doesn't apply here. Conclusions and future work. What I was hoping for when I started this was 70% to be plus or minus within 10% of the real estate price, and I thought that was kind of loose because for several reasons. One, I've never written any type of decision tree by hand before, and I knew the data. We're learning, it's the class, and it just seemed somewhat reasonable. So I did obtain on my best test conduction 67%, or within plus or minus 10% of the real price when using the log of the sales price. If you go back up and read some of the cited works that I have, one of the data scientists was quite pleased when he hit at plus or minus 15%, which is a 7.5% spread, using one of the standard R packages. So I was actually kind of surprised and pleased when I read that with my results. Most of the time I would say that I would not be able to write code as well, though. As far as what I really feel like it should be to be useful to the real estate industry, I would think 85% to be within minus 6% of the real sales price, and that's because you have to compensate for the realtor's fees. Missing on 15%, while not great, hopefully you would make up the loss difference when you exceed the sales price and get it right. As far as future work goes, I would probably attempt to use the Gini or the classification error for the best split, and compare with these results, and obviously use which of the three is the best. And then I would also attempt to start this, run this with the standardized R packages, because I'm sure that the people who wrote the decision trees are far more competent at this than I am, and would most likely have a much better hit rate, accuracy rate. So as far as the actual application, we'll run through a couple of quick examples. Here we go. Let's see here. Takes a minute to run through and initialize everything. It's building the model now. And UI, here we go. Alright, so here's a list of, or not a list of, here's the visualization of the reports, the distribution of the sales price we discussed, the distribution of the log of the sales price, and again, much more of a normal distribution. I guess maybe slightly skewed this way a little bit, but certainly not as obvious and blatant as just the distribution of the sales price. A couple other visualizations: distribution of sales price by neighborhood, and all these layouts came from ggplot2 website. It's pretty pervasive, not pervasive, but pretty flexible functionality. They give you some really cool options. I don't know, I like the color green, but distribution of sale price by sale type. So you have to go through and see what these map to, but new is obviously new construction, things like that. And finally, the correlation matrix again, like we discussed. You can see it's pretty strong correlations here. So we built a model. I believe we used overall quality, GR living area, but we didn't, obviously you would exclude total basement square footage and first square footage, because they're going to be very, very highly correlated to the GR living area. Also have a map of Ames here. I'll scroll down a little bit to see it in the size very well, but it's my first shiny application. And here is the prediction engine. So We have 56 properties that we can run the predictions on. And if you look here for number 1, this is the actual numbers it pops in automatically. It's the way Shiny works. This is what they call reactive processing. So as soon as this changes, these fields will all react. So we can go in here and just hit random 5. A little better, 90,000 is the predicted value, 130,000 was the real value, so I would still fail that test case. 8, hit it right on the button. 200,000. Let's see the last 56, 180 to 170. So that that falls within the range. We already saw 1, and let's do 32. Say 243.90. That's probably one of those ones that could have qualified as an outlier, but who knows. Anyways, so that's how it works. The other thing I would need to add ultimately would be exception handling. Didn't have time to get into it that much, but that is my project. I hope you've enjoyed it. I certainly learned a lot, and in the future I will be able to productionalize this and make some realtors' lives and some buyers and sellers' lives much easier. Thank you.